Okay, a brief look at how we did on the midterm for Physics 204 summer 2020, and a brief attempt at transitioning from that into tips and tricks for the final exam, which is due at midnight tonight. All right, first, the very first problem on the exam, the first part of it, you're given a differential equation in part 1a(1)(1). You're asked whether x equals x naught cosine of blah does or does not satisfy the differential equation given above. Almost everybody did get correct the fact that it does not. It does not. That is the correct answer. And most people did the right kind of work, which is differentiate that expression twice and see if, when you take its second derivative, the second derivative is indeed a certain constant times itself. What threw a lot of people is that they knew it would be if that constant up there in the original differential equation had been squared, right? A lot of people wrote me or very reasonably asked in class, like, are you sure you meant this, Yaverbaum? Was this really the question? Because I'm down with it if you just made a typo and then that term was supposed to be squared but wasn't. Very fair question, totally fair to be like very concerned whether that term in the original differential equation had been squared or not, because it would all work out if it were, and it wouldn't if it was. Okay, fair to wonder if I made a mistake, but then the answer is I didn't, right? And if you couldn't reach, you'd have to assume that I didn't if you want to take the test seriously. And here's the thing: if I had made a mistake, then we all knew what to do, and we would say that yes, it does satisfy, and here's why, because those two constants are the same. But if I didn't make a mistake, then what that just means is not that the question's any harder or any different, but just that the answer's false, not true, right? In other words, what most people intuitively did understand is that the kq over r cubed, that constant term given in the differential equation, if it had been squared, then this all would work out and satisfy. If it's not squared, it doesn't work out. So that doesn't mean you can't do the question. It just means that the answer is no, right? And what's the reason that the answer is no? The reason is because kq over r cubed does not equal kq over r cubed quantity squared. Like literally that, if you write that explicitly, because the constant term in the differential equation doesn't equal the omega term in the cosine function squared, then the cosine expression does not satisfy the differential equation. In other words, the very thing that everybody asked, not everybody, but a lot of people very fairly asked me about, are you sure that thing shouldn't be squared? That's the center of the question. So your ultimate reason, how you show that one thing doesn't satisfy the other, is you say, because this term here does not equal that term here, and they needed to for all this to work. You see, okay, anyway, so if you lost like a point or two, and if I wrote like how or why, it's because I needed to see somehow. Don't just go in a circle and say it doesn't satisfy because it doesn't satisfy. That's where it doesn't satisfy. The constants don't work out. All right, anyway, basically the same thing happened on the next question. Roman numeral 1, big, a little Roman numeral 2, there's now an exponential expression we're trying exponentials now. Is it or is not a solution? Almost everybody differentiated twice and saw that it wasn't, because this time because of a negative sign. Okay, so maybe almost everybody got it right, and I think most people actually showed their work correctly for this one. Again, you just don't go in a circle, give a reason for why it's not, but the answer was no and no. Then in 3 and 4, now it's a little bit tricky, because now what we're asking is the following trigonometric expression a harmonic oscillator or not? Now, granted, the differential equation that was given is still sitting there at the top of the page, and that is having impact on one's mind and on the question. But here we're specifically asking, is this thing a harmonic oscillator or not? Which means it doesn't have to satisfy the equation above necessarily. It has to satisfy something of that form. Like, basically what I'm getting at is the answer for 3 and 4 were yes and yes. And again, most people did get this right. If there's 4 cases that have been given here on page 3, if there's 4 things, yes or no, yes or no, yes or no, and yes or no, then it really did go no, no, yes, yes. And most people got that right. You just also have to be clear now, if you're going to say that these things are harmonic oscillators, which they are both, 3 and 4, they are both. They both satisfy a differential equation of the form given above, although the constant might be different. Then you're supposed to show what the period is, and for each case. And that's that you can do that because for any harmonic oscillator, this is always true. And the omega in both cases is that term sitting right before the t. So you did have to work out that extra step to answer this. And this, most people did, but you have to do that in order to complete the question. Okay, and so if you lost points, it may be because you didn't solve specifically for t in both cases. Oh, all right, and very quickly too, what is t? Well, it's, in this case, would be 2 pi over r squared over, sorry, excuse me. I mean 2 pi over k, and then the r cubed comes up on top. And you do want to at least make that simplification. I mean, I'm picky to some level, but once you're solving for something like this, you don't want to have a fraction within a fraction within. I mean, you got to have it at least readable. So flip that denominator up to the numerator to show you know what you're doing. And you might have lost a point if you didn't simplify this fraction to that level, but most people didn't, and most people did. I mean, most people did, and most people didn't lose any points. All right, so that's number one. Oh, now this one here, I just want to say, okay, here, maybe I was picky. This is supposed to be this is to show the whole, that you get the whole concept. And I don't even know. The point is here, well, oh, I know. The concept here is to make sure that we're all down with something we really tried to emphasize when we first walked into that differential equation and had to treat it somewhat gingerly. This is the harmonic oscillation one, is we have to remember the difference between just any old equation that has a derivative in it versus a differential equation. The whole point of this is much easier to work with than our harmonic oscillator. Like our harmonic oscillator is a second order differential equation. That's not the first thing anybody would introduce if they were just trying to teach the math of this, but it's the first thing that we encountered in physics. So we're dealing with it. But just so that we can make sense, we're trying to back up and realize what would be the easier version of something like this. Is it really that bad, or what does it mean? And I'm really trying to show in the end with this up here that this is a differential equation. But in a non-trivial way in which this would not be, right? It is, you don't have to do any techniques of differential equations solving to solve this latter thing that I just wrote. It's this former thing. It's when the rate of change depends on the dependent variable that we have issues and have to think. And the thinking that I wanted to see right here, the one step that I think we did go over in class a number of times is, look, multiply both sides by dt, because in fact you are allowed to, and it does make sense to, and say, and then divide both sides by x. So in other words, collect all those x terms. This thing is just here for no reason. Okay, and then differentiate both sides. That's how you get ln of x equals negative omega squared t plus c. And that's the final thing. I mean, this is an indefinite integral. I should probably have defined what c was in order to make you be able to solve for c in a nice, easy way. But there is a c no matter what. Like, we do have to recognize there's going to be a plus c on the right side of this. So it was 1 or 2 points if you didn't deal with the c at all. And it was 1 or 2 points off if you just wrote down, well, to continue this, it's true that you end up getting something like this. But if you just write that down for no reason and then check and show that it's right, that lost points. Can you say, we guess this and then check? Yeah, you have to, but you can say this is a guess and then we're going to check, because that's what we could do with second order, with differential equations. But you have to at least, excuse me, even if you're guessing because you think it's a legitimate thing to do in math, which it is, but then you have to say, this is a guess. You can't just write something down just because we know that it's the answer and like without justification. So people did lose points here if they literally just wrote down something like that without any basis, such as the one I gave. And they did lose a point or two if there was no acknowledgement of the arbitrary constant c. Okay, that's what happened there. I'll try to move on. I'll try to move faster now too, but now we get to the dot products and the cross products, and hopefully you guys see that these are important and maybe tricky. It's really important to get inside and understand these, primarily because the cross product, which is such a bizarre mathematical procedure, right? It is bizarre and it's intricate. Like, to do a cross product, it's sort of amazing how computation heavy it can get. and then it turns into the right hand rule thing, which is a very obscure, unexpected kind of tradition. Um, but what I'd like everybody to see in the course is that this all comes around because in the end, the core of the magnetic field is itself a cross product. And the force exerted by the magnetic field on any moving charge is a cross product. It makes for field lines in the universe that don't point in the same direction as the things that are creating them or the forces that they create. Very intense implications and very hard to get your mind around unless you're a little bit practiced with it first in the strict mathematical sense. So I need people to understand what's going on with the cross product and why it yields, how all those computations mean perpendicularity in the end, they do. So I was picky here. I mean, to get straight to the chase, I mean, first of all, there's like 4 exercises here, each of which is worth 4 points. I should make that clear again in a second, sorry. Every little exercise of this whole part 1 was worth 4 points, okay? So you could lose, you could only lose 4 points if I literally could not find the exercise answered anywhere. If you tried to answer it all, you got at least a point for every bit here, okay? But these 4, they are heavy enough that each one of you needed to have like made it clear I'm doing this one and then get an answer and circle it. And there had to be work in between because nobody just knows dot products in their heads. I mean, like to arbitrary questions. So I did need to see 4 explicit questions. There's no doubt there's no way that this one doesn't take more work than the 2 above it. It literally has to take at least an extra step, right? Because there's a cross product in a dot product. It has to take at least one more step than the thing above it. Even if a lot of you know a cool trick for, if you know a cool theorem or a cool result that says this is actually equivalent to something else, that's great. But then you have to write that theorem down. You at least have to say that, right? In other words, what I'm saying is there were some cool tricks and techniques that people used to get this complicated one here and the one after it, which I was hoping. I am asking questions in hope that people will see, oh, that's not as bad as it looks. I can like finesse it like this. All great, all great. But it is a finesse if you finesse it, right? If you reduce the computation of this, it's by virtue of some piece of knowledge you have or some technique that works. It must be explicated. So I'm saying this. I looked at how much work was done for each one of these. You can do the top one, and the answers are like 100 and then 0 or 0 and then 100. And then like, I mean, they're all in the answer sheets, but then like 10I hat plus minus 10 J hat minus 10 K hat or something like, actually, and then the last one I think is, actually, I'm not going to pretend I remember the answers. I'll look them up in a second. But the point is, there's whatever amount of work you did for the second one has to be more than a line. It's a cross product, for God's sake. I mean, even if you did the computations at one point on rough paper, then you copy them down on the final. But the second one has to be at least 1 line long because it's a cross product. So then the third one has to have 1 extra step acknowledged at least compared to the second one. And a lot of people didn't have that. They had the exact same computation for both. I don't see how that makes sense. If you use a determinant of a matrix or something, and many of you may not know what I'm talking about, and that's totally fine. Like if you just learn this from me and you do it my way, cool. But if you have another way of doing cross products, such as using the determinant of a matrix, I'm all for it. Like some of my best friends are matrices. I love matrices. I love determinants. I get how it works. But it took me a long time to get why that's equivalent to this, even if you find that one easier. Like no matter what you do, you have to show how it ultimately makes sense. Like, so our cross product way comes back to the definition. The matrix way is fine, but at least somewhere next to it, like if you're using determinants, then write down a simple like write down something like, right? Like if you're just going to introduce a determinant, since I've never introduced it in class, I don't know exactly what it is or how it relates to anything. So at least define it and say, this is how it relates. So therefore, when you're doing the cross product can be used this way or something. Anyway, so people did lose points here in sort of a picky Yaverbaum. Like I'm sure there are many people who got the third one right, but still lost 2 points for showing work or something like that. This is why, okay? And again, in the back of my mind, I mean, we all know, of course you can look these things up. So since you can look them up, show that what you have written down is more than just a lookup. It comes down to that. Okay, but it was like 2 or 3 points. Then this next one, and you know, I don't love, there's aspects of this problem. They're sort of messy, like the very presentation of it. First, it asks for a clear free body diagram. Okay, a lot of people, okay, it asks for a free body diagram. I am totally psyched for any picture that anybody gave me of like, here's the string, I'm labeling it, here's the mass. That's cool. Okay, that's as a picture. But now a free body diagram is just supposed to be the forces acting on some point mass, right? So you wouldn't put a string with its measurement in a free body diagram. You would put something representing tension or something like that. Free body diagram could look like this. Sorry, I'm being very slow. A free body diagram, like you could give a diagram to, so that I am clear on which way your pendulum is sitting at any moment. Like if you just give me a picture like that, I'm like, okay, so they're picturing a pendulum at the right side of equilibrium at that arbitrary point in their swing. Okay, cool. So then their free body diagram could look like this. Okay, totally full credit if you just drew that. That's a free body diagram and it's right. It's tension and gravity. Or you could start making use of that free body diagram for sure. You could do what physicists do in order to start breaking, you could start breaking it into components. You could break it into components. And by the components, therefore, have it lined up, have it all worked out so that you can write down an F net equals MA statement for each individual axis. I'm all for it. And that diagram would look like this. According to this picture, that diagram most probably would look like this. And this would be mg cos theta, assuming that this is theta here, like assuming this theta, which is why that picture is good to do, because it makes the free body diagram clearer. And this would be mg sine theta. Okay, if the original picture is flipped, then T should be pointing the other way. If you don't have an original picture, that's technically cool. All I asked for was a free body diagram, but your diagram has to be self-consistent. Here's where I took off points that I'm sure everybody's mad and feels I'm being obnoxious. But if you had a diagram that had mg sine and mg cosine and mg in it, even if everything else about it is basically correct, if you have mg and mg sine theta and mg cosine in the same diagram, that is wrong. And I know there's many different traditions of how to draw these things, but if you really look back at any of your notes from old classes, sure, some professors will do the mg thing and some will do the mg sine, mg cos thing, but you can't have them both in the same diagram. It defeats the whole purpose. Like I don't want to get too bogged down in it, but mg sine theta plus mg cos theta vector-wise equals mg. It's two different equivalent ways of counting the same force. If you put them in the same diagram, you're double counting the force. And if you're that loose about the diagram, it defeats the whole purpose of the diagram. The wild thing about free body diagrams and field line diagrams, you know, for our ultimate test, is that actually, if you put enough care in the diagrams, they are computational tools, precise tools. They do the computation for us if we believe the diagram. But if we take the diagram not seriously, then all computations that follow from it are actually wrong. Okay, so this is my little thing, but don't put, whenever you break something into components, then that is an equivalent way of saying the original thing. And you can't say it twice, you can't count it twice in the same equation. But all right, anyway, so people did that, so I was a jerk about that. Then just read the questions carefully. Most people got this next one about angular frequency correct. Like omega simply is the square root of the term in the function. I mean, omega is pi over 4. And then you just work that out to 4 digits as I asked, just because I want to get a real number. So it's like 0.785 or something like that. And then how many cycles per second? What this question 3 is asking is frequency, right? Technically, question 2 is asking you for omega. And then 3 is asking you to convert that to a standard frequency measured in hertz. It's asking you for how many cycles per second. So the answer to that one is like 0.125 hertz, I think. Like, yeah, 1/8 of a cycle per second. You can't say 8 seconds per cycle. Like, that's true information, and that's one step away from actually answering the question. But if you say 8 seconds per cycle, you're not answering the question, right? So I would take off a point for that. Like, you have to bring everything back to the actual question. And then similarly in 4, and 4 may be the hardest question on the whole page. Although interestingly, someone asked me about it in class, and I think I showed it in class. But it is hard. It does involve work. But what we're being asked for in 4 is the particle's approximate speed at a certain time. Luckily, I don't think most people got thrown by the time part. They plugged in. But yeah, speed means the magnitude of velocity. The only way to get velocity is to differentiate the position function And technically, we don't have a position function. We have an angular position function. So you did have to go through these steps where you differentiate the theta thing, and then you multiply by, or you divide by r, sorry, you multiply by r to get a velocity, and then you get an answer with a negative sign in it, and you do have to read the question, realize, okay, it's just asking for speed, which sometimes is what we want. So you get rid of the negative sign. The ultimate answer to this one is approximately 0.411 meters per second. Okay, and a lot of people got it right. And sometimes I was a little bit intense if I thought they just skipped a lot of steps, because there are a lot of steps to show here. And yes, in the end, your answer should not have a negative sign in it, even though the velocity is negative. Just remember, it's asking for speed. It's not asking for angular speed, and it's not asking for angular position. It's asking for speed. So that's what you want to get there. And then five was like walk through the proof that you spent a lot of time in lab, and it is a proof. You have to do it. It is fairly short. It is, all the steps are almost laid out for you. If anybody who basically showed that they knew what proof I was asking for and did it, I gave full credit to, but you had to do something. I'm going to go on. All right, then, oh, and sorry, for that one, every single part was worth 6 points, up to 6 points. So if you did the part at all and I could find it, you certainly got at least 1 point, probably 2. And then if I thought you did it like super wrong, you might lose up to 4 points. But each one of those parts was 6 points. The whole first thing, each one was worth 4 points. Now we get to something where there's 3 big sections, and each of the 3 big sections is worth 10 points. The first section here about gravity, okay, it gives you all this verbiage, which would be a lot to assimilate for the first time on an exam, but you've seen this problem before, and the bottom line is you're supposed to, given the situation, you're supposed to derive a magnitude of some force as a function of radial distance from the center, okay? The bottom line is, to do this, you have to do all these computations, which most of you did, computations that ultimately assume this. I mean, the vector part is not really the, okay, I'm putting the vector part to be technical, but okay, the ultimate thing is that here, to get the full net gravitational force exerted on any particle at any arbitrary spot, like anywhere in the plum pudding of all this solid sphere, right? There's like mass everywhere, and we're some arbitrary spot here between, between the center and the edge of the sphere, excuse me. Okay, we're looking for the net gravitational force at some point arbitrarily located within the solid interior of this uniformly dense structure, sphere. And so the idea is that gravity is pulling on us from every direction right at this point, like all this mass. Like all this mass here is all pulling on us from there. And all the mass like here is all pulling on us in the opposite direction. There's all this mass pulling everywhere. And it doesn't all cancel out. There's a net effect of all of it on us at this arbitrary point somewhere. It turns out that in order to get and so it's amazing that we can find it at all. Like every single point of mass in this whole structure is pulling on us in all these different directions. And they're all tugging and pulling and pushing. And yes, creating one big vector sum. So a lot of cancellations occur, but not entirely. There's a net effect that we're trying to figure out. And the amazing insight is, it turns out, if we think of ourselves as standing between 2 big chunks of mass, like we're standing in between all this mass that's above our head and all the inner sphere mass that's below our feet, all of it's pulling on us. But yes, it turns out that if we just figure out the total effect of all the mass underneath our feet, if we just figure out the gravitational effect of all that, as long as we know what that is, it turns out that gives us the answer, and that's awesome. But why? Because we can discount all the stuff above our head, that whole shell. In other words, we're standing between a sphere and a shell, and the net gravitational effect of a shell equals 0, and the net gravitational effect of all the things underneath our feet equal that as though from a point mass. So you have to say that. So you have to say the sum of the whole is the sum of the parts. The two parts are stuff above our head and stuff below our feet. The stuff below our head all works out to 0. Now, I'm not even asking you to prove that. That's like a whole thing in itself, but it is a discovery or a claim or a step. It's certainly not self-evident to me that all the stuff above our head all actually balances out to 0 because it's a spherical shell. Therefore, we're left with the stuff below our feet, and that's what we do the whole calculation around. Okay, and so we do this whole density thing that most of you did and is great, and we plug in, right, just like Gauss's law. But you have to recognize that's what's going on. Like, in other words, a lot of people lost 2 points because they just went straight to this step and did all this work to plug in a certain amount of mass into that step, but never acknowledge, basically put it one way or the other. You either literally explicitly have to acknowledge something about the shell that is there, but is all equaling to 0, or put larger to explain what you're doing while you go. You can't just write raw math statements down like they're self-evident. Even if I can read them, what is the structure behind this thought? The structure is the whole is equal to the sum of its parts. We're standing between two parts. One part, it turns out, equals to 0, and the other part we're going to solve for, and that will be our answer. Okay, so you gotta just acknowledge everything. That's the best way I could put it. People lost 2 or 3 points here. If I wrote how or why or shell, that's why I did that. Okay, so that was that. Then you're supposed to plug in numbers to your result and get a number. Almost everybody did this great. I mean, and the ultimate answer that you were looking for this part B, all of which was worth 10 points. The ultimate answer is approximately like T over 2. The amount of time you're looking to get to the other side ends up equaling approximately 53 minutes, 53.7 or something minutes. It does ask for minutes. You got to convert to minutes. As long as you did a bunch of work and got that answer, like that is the answer and you got full credit. But you had to plug in these numbers. Like you at least have to read the question enough to know, yes, this is the spitting image, the exact question we asked in the practice exam. I just changed the numbers from Earth to the moon, just so you could walk through the calculation and show that you knew what it was. Right? And so some people totally just did the Earth thing again, hopefully because they innocently just misread the question not carefully enough, and therefore they did lose points because the point is the moon. But be careful too, like this is the kind of thing you don't just want to blindly do what you did on the practice exam, because it can look like some form of cheating or something like that if you literally just put a bunch of physics work down that does not actually answer the question. I don't think that's what happened. And anyway, if you didn't do the moon, you lost points here. And then C is also the same answer for sure, but here the whole point of this is that you have to show why or how. Each one of these chunks of the gravity question is 10 points. And I think I was generous in the sense that if you were in the ballpark at all for any of the proofs and you didn't miss these crucial steps that I noticed, I'd give full credit. But this last part, you cannot just say all simple harmonic. Well, first of all, you can't just write down 53 again and be done with it. Some people did. That is definitely not worth 10 points. If you literally just wrote the same answer again, I probably took off 7 or 8 points. If you said something like all harmonic oscillators have the same all harmonic oscillators have the same period or something, well, you're on the right track. You're showing that you get what I'm asking here, but you still might have lost like 7 points or 6 if you just wrote down simple harmonic oscillators have the same period or something. That is not sufficient. First of all, the point is that simple harmonic oscillator doesn't change its period based on amplitude. That the essence of a simple harmonic oscillator is a period independent of amplitude. Like no matter how wide the space is, the time cycles are still the same. Yes, that's the insight of this. Yes, that is worth saying. But first of all, you have to say at least that. It's not that all simple harmonic oscillators take the same amount of time. Like if I have a bigger spring than you have, my spring will take more time to do its cycles. It's that given the same simple harmonic oscillator, the same K and M, or the same L and G, with the same physical parameters, if you have a simple harmonic oscillator or two identical oscillators with the same physical properties, the same omega in effect, then no matter what you do to its amplitude, the period will be the same. But the whole point of this question, the exciting result, is to prove that even if you pick an arbitrary tunnel somewhere through the Earth, an arbitrary tunnel will still have the same omega as the diameter tunnel. You have to show that. It's possibly the trickiest thing to show in the whole exam. I would think it would be an outrageous thing for me to ask you to show cold out of nowhere, but we did do it. Like, I mean, I do want you to know this thing. And the real way to show, I got some great questions about this in class when we went over it. People were looking at the diagram that I passed out, because I think the diagram is like vital to picture this and then explain it. So I passed out that diagram in class, and people asked some really good questions looking at that diagram, like, wait, I don't get why R would change if L, like showing that they were really linking the diagram in their minds, or trying to the whole concept I'm saying. It shows how important the diagram is, and it shows that, it's not just a random sketch. It's a point of a diagram, even when someone doesn't literally ask you for one. If you're ever trying to explain something, which you are in this whole exam, and by the way, I sound so mad. I don't mean to be sounding mad at all. I'm just sounding intense. Because people did well, really. Oh, yeah. If you're trying to show something, a diagram is a crucial way. So is English. But for a lot of us under pressure, English seems harder to get grammatically correct in the middle of math thinking. But a diagram can show tons, as long as what the diagram actually does is include a label for every quantity that, if this diagram includes a piece that is labeled for every variable that's mentioned in the whole proof that you're trying to do. In other words, if you're trying to show something here about R and sine theta or whatever, the purpose of a diagram is to show what the heck you mean by theta and R, right? The diagram is actually the definition of the variables and constants that you're using to make a mathematical point or a physical point, anything like this. But I'm saying, to get full credit on this last one, you really had to draw a diagram that actually was not just like a circle, here we go, this is the situation. You had to draw a diagram that had theta and R labeled in it, at the very least, in a way that I could read, so that even in the absence of a good, clear English sentence, I could follow your proof and see that you were showing me how this works out to the same harmonic oscillator as the one above it. So a lot of people did get full credit, but it was easy to lose credit on this one as well. You could, if you didn't acknowledge at all the question, you could lose 6 or 7 points. But if you did it, but it was like kind of, I thought you were just, if you showed me that you knew what page of your notes we were talking about here, but you just sort of copied from your notes, that's where we're looking for the difference that makes a difference. Not to be picky again, but the answer, yes, was 53 minutes again, and it's because in the first case we have this in effect. And in the other case we have in one case we have blah, blah, R, and in the other case we have blah, blah, X, and it turns out X equals R sine theta. But that's not even the important thing, is that either way, we have a harmonic oscillator based on a displacement variable where the constant is the same. That's what you're trying to show, that the constant is the same, therefore the omega is the same, therefore the period is the same, regardless of the fact that one is R and the other is X, therefore one is like a shorter amplitude than the other. But okay, that's that test. And what time is it? Hold on. I'm actually going to try to post another quick video that addresses the actual final exam you're taking now. And I know the clock is running out, but hopefully you're doing other things, to get yourself ready and stuff. This hopefully gives you an idea of what the way I'm looking for you to answer questions on the final exam. I actually will try to post another video that specifically will try to tie together magnetism with electricity to make sense of the whole thing, and therefore enable everybody to rock that extra credit if they want. I mean, it's extra credit because I didn't get to that punchline in the regular schedule. Therefore, you're being tested up through magnetism, but how E and M fit together, which is sort of the exciting result of all this, I'm going to try to tell everybody in the next lecture and therefore award everybody with extra credit for trying to make some sense of it. But the material ends with magnetism. The final exam you have answers for or solutions for. So hopefully this will at least help in the day that we have left to help you tighten up whatever work you've already done and make it as presentable as possible. Just make your document, just pretend that your final exam is itself like a paper that you're submitting on having discovered all these concepts. Like make it pretty, make it, you know, put pride into it. Just wherever you know something, strut your stuff by dragging it out as clearly as possible. And when you don't know something, compensate by making what you're saying as clear as possible. The irony is the more picky I can be with your work, the more I could find little like, oh my God, she dropped a negative sign. Oh my God, the more I can find tiny, tiny little errors, that means the more you've really shown me a huge, precise bulk of material. So the more I could here and there find a point or this, and that actually means you're doing that much better on the whole, right? You don't want to put something that's so vague that I just have to write things like what, show, question mark, you see, anyway. Okay, I will try to talk more about the rest of the physics and post that, but that will be for the purpose of extra credit and stuff like that. I think hopefully it's not too late for this to help you somewhat. So we thank you for your support. Live long and prosper.